Hello everyone, I am Jay Patel, a B.Tech AIML student from CHARUSAT University, and today I will be presenting design of digital comparator, also known as Magnitude Comparator, as a part of my digital electronics course. In this presentation, I will explain the concept, design, working principle, and application of digital comparator. Let us begin with the introduction to digital comparator. Why comparator matters? Digital electronics mainly processes information using binary data, that is zeros and ones. In many computing or many digital system, comparing data values is necessary for decision making and for decision making operation. For example, a processor may need to check whether one value is greater than the another value before executing an instruction. Digital comparators are fundamental building blocks that perform these comparisons and help system determine relation between binary numbers. After understanding the importance, let us now define what is a digital comparator. So a digital comparator is a combinational circuit. Since it is combinational, it does not store past information and the output depends only on the present input values. The circuit compares two binary numbers, usually A and B, bit by bit process. It produces three output indicating A is greater than B, A is equals to B, or A is greater than B. Now that we know the definition, what is a digital comparator, we will move on to next slide of different types of comparator. So what are the types of comparator? One bit comparator is the simplest form that compares and represents that compares a simple one single bits number. Now let's move to 2-bit comparator. So a 2-bit comparator compares two binary numbers containing 2 bits each. In general, n-bit comparators can compare binary numbers of any size. Although circuit complexity increases with higher bit width, the fundamental comparisons logic remains the same. Let us now study the design of 1-bit comparator, which forms the basic building block. So in 1-bit comparators, A and B are two input variables. The circuit generates three output corresponding to greater than, less than, or equality condition. When A is equals to 1 and B equals to 0, so A is greater than B. When A is equals to 0 and B is equals to 1, A is greater than B. A is less than B. Equality is obtained using Z-NOR operation, which produces a high output when both inputs are identical. Using these all conditions, we derive the Boolean expression required for the circuit implementation. Based on this expression, let us now observe the truth table. So this slide shows the truth table for 1-bit comparator, where each rows of A and B represents their along with their outputs. Both inputs are equal when both inputs are equal, the equality output becomes high, as you can see here. When A is greater than B and the greater than output becomes high. Similarly, when A is less than B, the less than output becomes high. Using this information, we can now implement the circuit using logic gates. So here in this slide is about logic circuit implementation. Not gate generates complemented includes A complement and B complement. AND gates generate A greater than B and A smaller than B conditions using complemented input. The Z-NOR gate determines equality because it output logic 1 when both inputs are the same. By combining this logic with all OR and NOT gates, we can obtain the complete digital circuit. After understanding this 1-bit implementation, let us extend our topic to multi-bit comparator. So here in this slide I will explain 2-bit comparator concept. So in a 2-bit comparator, we compare two binary number A1 A0 and B1 B0. The comparison begins with the most significant bit MSB, and since it has higher priority, if the most significant bits are equals to the least significant bits LSB are compared. The final result on determines the highest unequal bits, which may this a cascade comparison approach. Now let us look at some practical applications of digital comparator. So digital comparators are widely used in modern digital system. Like in a microprocessor, comparators help execute and conditional circuits. Like let us take an example. When a program checks whether one value is greater than another using an if condition, the comparator performs that comparison internally. Another example is like that of memory systems. In memory systems, comparator are used for address matching. When the comparators request data from a specific memory locations, a comparator checks whether the requested address matches the stored address before receiving the data. It also helps in sorting circuits. So comparators compare numbers to arrange them in ascending or descending order. For example, hardware sorting units compare values step by step to organize the data efficiently. Also in digital, it also helps in digital system, enables digital logic for control and automation. For instance, in a temperature control system, the measured temperature is compared with a present reference, and if it exceeds the limit, a cooling system or alarm is activated automatically. Therefore, digital comparators plays a crucial role in computing data progressing and intelligent control. Now let's move to next slide of advantages and key takeaway. Digital comparators provide fast operational because propagation delay mainly depends on logic gates level. So the design is simple because only basic logic gates are required. These logic gates are highly reliable because output depends only on the present input without memory. Due to these advantages, it is highly reliable. They are highly because output depend only on present inputs without memory effect. Due to these all advantages and wide applications, comparators form essential components in arithmetic logic units, memorable management systems, and digital control circuits. Now let us move to next slide. So in this slide, we will discuss about the limitations to consider. One limitation is that digital comparators are designed specifically for binary inputs only. Therefore, they cannot directly process analog signals or other number system without conversion. Another limitation is scaling challenges. As the number of bits increases, the required number of logic gates also increases, making the circuit more complex. Additionally, it is the limitation are hardware requirements. As the number of larger comparators requires more hardware components and routing spaces on the integrated circuit, which may increase power consumption and design cost. Now let us understand how comparators work for larger binary numbers. So an n-bit comparator, n-bit magnitude comparator extends the basic comparison concepts to multi-bit binary numbers. Instead of comparing single bits, these circuits analyze entire binary words simultaneously. It determines whether one multi-bit number is greater than or equal to or less than the other. These comparisons are constructed by combining several smaller comparators units using cascading connection. This cascading approach allows comparisons of numbers with an desired bit width. This is the example shown in the image of cascading width. Now to better understand this, let us examine the block diagram architecture. So the block diagram shows a modular and a cascaded structure. Individual bit operators comparators are connected sequentially where each stage is compare corresponding bit of input numbers. The comparators start from the most significant because it has the highest weight in a binary number. The most significant first processing improves decision efficiency since a difference detects at a higher bit immediately determines the result. Now let us understand the working principle step by step. So first, the comparators begin at the most important and the start at the MSB. Since the MSB carries the greater value, it is checked first. If the both MSB values are equal, the circuit proceed to the next lower bit position. As soon as differences between bits are determined or detected, the comparison result is determined as greater than or less than. Finally, the result propagates through all the stages to generate the complete output signals indicating A greater than B, A less than B, or A is equals to B. Now let us look at the simple real world example to understand comparators usage. One example is comparison of student grades. So a system can compare marks of two students and determine who score highest. Another example is calculator logic. Scientific and financial calculators internally compress numbers using operators such as maximum value selection or conditional calculation. Comparators are also used in system monitoring applications. For example, temperature sensors continuously compare measured temperature with predefined threshold, and if the limit is crossed or alarm is raised or cooling system is activated automatically. Now, instead of designing comparators only using circuit gates, integrated circuits are also available. So, IC 7485 integrated circuit is a widely used 4-bit magnitude comparator and is considered an industry standard solution for digital comparison operations. This IC compares two 4-bit numbers directly and simplifies hardware design. Multiple 7485 ICs can be cascaded together to compare larger binary number, making it highly flexible for the practical digital system. Now let us look at the importance of these key features of IC 7485 chip. Let us now look at the important features. So the IC 7485 is a 4-bit comparator that is capable of comparing two 4-bit number labeled as A3 labeled from A3 to A0 and B3 to B0 against each other. It provides three output, that is A is greater than B, A is equals to B, or A is smaller than B. One more important feature is its cascaded design, which allows multiple ICs to be connected together for higher bit comparison. The device also supports high speed orientation and is fully compatible with TTL logic families, making integration into digital systems simple. Due to these all features, IC 7485 is widely used in the manufacturing or microprocessor control system and digital data processing. So thank you. With this slide, I would like to conclude my presentation. Thank you for your time and attention. I hope this presentation helped in understanding the design and working of digital magnitude comparators.